Okay, so team, today we will cover the greedy technique. Okay.
Professor,
Yes, yes.
I can't hear you very well. I don't know if it's my side or your side.
Okay, let me pull it back. Yeah, can you hear me now, Stacy?
Not, oh, hold on. It's it. My husband had headphones plugged in. It was on my side.
Okay, okay.
Sorry about that.
Great, great. So today we will cover greedy technique. So till this point, we have looked at a lot of DP problems, right? If we have time, we will come back to DP again, right? And cover one or two more problems, hard problems. But let's cover more topics, right? We still have greedy technique, backtracking, and NP problems. Backtracking and NP problems will not be there in the final exam, okay? Will not be there in the final exam. But apart from that, all other topics will be there, right? Okay. Now let's start with this greedy technique. What exactly is this greedy technique? And how is it different from the other techniques we have seen, right? Divide and conquer, DP, and so on. Okay, let's start. So this greedy technique works on a class of problems called optimization problems. And what are optimization problems? You want to maximize something or you want to minimize something, right? Okay, for example, knapsack. Knapsack is an optimization problem. There you were trying to maximize the total value, right? So that's an optimization problem. Okay, what is the core idea behind greedy? You know the concept of greedy, right? So you want the best, right? You want as much as possible, or you want the best, something like that. Okay, applying that concept here at every point in an algorithm, in a computer program, you will have to take some decisions, right? Suppose you have to take a decision at this point, and you have 5 or 6 choices in front of you. How would you choose? So greedy technique says choose that option that maximizes or minimizes that particular step. Suppose you're working on a maximization problem, choose a step that maximizes the value at that particular step. And similarly, in the next step, among multiple choices, choose that value or that step that maximizes the value, and so on. Keep doing this until the dead end, right? That path itself is the solution. That is the core idea behind greedy. So what is the biggest assumption in greedy? You are choosing a step that is locally optimizing things, right? That's a local optimization. You're choosing the one that maximizes or minimizes at that decision point. So the assumption is that local optimality leads to global optimality. Is that true? Is that always true?
No.
In some cases, it is true, but it's not, right? In every situation. So consider life. We try to say maximize happiness in every step. Suppose we do that. Does it lead to global happiness or contentment? No, right? Because a kid might want to play all the time. So, so if you choose that greedy step, right, the best option at that step is, right, the child wants to play. But suppose you make sure that the child studies, or right, at a young age, that is the one that leads to global optimality, right? So local optimality does not always lead to global optimality. So sometimes whenever we have multiple choices in front of us, right, we might choose one step that really hurts us at that point. Why? Because maybe we are thinking about global optimization. So this is the biggest difference between greedy and dynamic programming. In dynamic programming, we care for global optimization. Hence, we choose a step, right, that need not optimize locally, but it will definitely lead to global optimization. But greedy, it doesn't care. You always choose a step that leads to local optimality. Make sense? Okay. Now let's start with cashier's algorithm. So we will majorly cover 3 problems, 1 simple and 2 complicated. Okay. So here is your problem. A cashier has an infinite supply of coins of denominations 1, 5, 10, 100. This is just an example, but you can always generalize this later, right? Devise a method to pay any amount n to customer using fewest number of coins. Remember the min coins problem that we saw in dynamic programming? It's the same problem. You want to make change for amount n using a couple of denominations, and you want to do it in fewest number of coins. Okay, so let's take an example. So here is our example. Say 1, 5, 10, 100. These are the coin denominations. N is 128. You want to make change for 128 using these denominations. You have an infinite supply of these coin denominations. Okay, min coins is 7. See, like, what is the simplest idea? What does a cashier do at a bank? Typically, what they do is they look at the maximum denomination. They remove from 128 as many copies of that maximum denomination, right? So you can remove 100 only once. Okay, you remove it. So you have 28. Then remove from 28, right, a number of coins of the second maximum denomination. You can remove 10 and 10. So you can remove 20. You cannot remove 3 times 10, right? Okay, the remaining amount is 8. Then remove from 8 the number of coins of denomination 5. You can only remove 5 once. Remaining is 3, right? 1, 1, 1. Make sense? So this is how most cashiers give change. Now, can you tell me, does this always lead to minimum number of coins? Right?
Not necessarily.
Not necessarily. So for this example, it worked. But for another example, it might not work. But what is the idea here? This is a greedy algorithm, right? So you see that 128 is greater than 100. So remove from 128 multiple copies of 100, maximum copies of 100. Then take the difference, 28. Remove maximum copies of 10, right, from 28, so on. So this is a greedy algorithm. At every step, you choose a coin denomination, right, the maximum coin denomination that is less than or equal to that current value of n, and remove, right, from it. So this is a proper greedy algorithm, right? So we will analyze that here. Here is your greedy algorithm, the pseudocode, right? So we will assume the coin denominations are 1, 5, 10, 100. And sort these coin denominations in, say, decreasing order. Our priority is 100 first, and then 10, then 5, then 1, right? So in decreasing order. So you have 100, 10, 5, 1. And what is A here? A is the, can you tell me what is A here? A array?
How many of each coin you have?
Right, the copies of that denomination. A1 is the number of copies of C1, AI is the number of copies of CI. So you have a simple loop for all coin denominations. If n is equal to 0, you break, right? Else, you find the number of copies that you want. A of I is n divided by C of I, and take the remaining amount as the next n and repeat. Min coins is the sum of all copies of or instances of C of 1, instances of C of 2, right? Copies of C of 3 and 4. Of course, I mean, this is a loose pseudocode, but you can generalize it for different coin denominations and many other cases, right? So I have tried to simplify this code a lot, but you can generalize it later. Make sense? Okay. The problem is that for this example, you will definitely get optimal coins, that is min coins. For that, if the coin denominations is 1, 5, 10, 100, for any value of n, you will definitely get optimal minimum number of coins. In fact, if your coin denominations is 1, K1, K1 times K2, K1 times K2 times K3, so on up till K1 times K2 times, so on up till Km. If these are your coin denominations, there are how many? M plus 1 coin denominations, right? Then you will also get an optimal algorithm. It will definitely lead to min coins. However, let's choose another set of coin denominations, 1, 3, 4. 1, 3, 4. If you choose 1, 3, 4, let's see. Suppose you want to make change for 6. What do? 4 plus 1 plus 1. You cannot use a 3 coin here, right? 4 plus 1 plus 1. It's 3 coins. You use 3 coins here. The optimal would have been 3 plus 3. Just 2. Min coins is 2. So in this instance, you did not get optimal solutions, right? You did not achieve minimum number of coins. Okay, let's take another case, which is more beautiful. If your coin denominations are 2, 3, 5, suppose you want to make change for 6, what happens here? You remove 5 and you want to make 1 change for 1, but making change for 1 is impossible. So,
question, Professor.
yes.
So here actually, if the given problem is for any n, then n equals to 1, this problem has no solution, right?
Right. Correct. Right. So for this set of coin denominations, right, for n is equal to 6 or n is equal to 1, or in fact, n is equal to multiple of 5 plus 1. And maybe there are hundreds, I mean, infinite number of combinations, right? It is impossible to have any solution. See, not just non-optimal solutions, you cannot have any solution. It's not possible to solve the problem, right? You cannot make change at all. So we say that, right, it's infeasible or unsolvable. I mean, for this instance, not the entire algorithm, right? For this instance, it's not solvable. You did not make any change. So what does it tell you? So here greedy is not even working. Leave optimality. It is not even solving the problem in some cases, right? At least for this coin change problem, you can use the greedy approach, but that approach for some instances of coin denominations will not even give you any solution. leave whether it is optimal or non-optimal. It is not even giving a solution, right? So this means that this greedy approach will not always work. It's not as powerful as divide and conquer or dynamic programming. You can use it for a lot of problems, but greedy algorithms exist. There are only a very few problems for which greedy algorithms give you optimal solutions. And luckily, those have been very important problems. Apart from that, it's too difficult to know, right, whether greedy works or not. I mean, it's not that difficult to know, but the point is, uh, it's rare that greedy gives you the optimal solution. That's the point, right? It is rare that greedy algorithm gives you the optimal solution. And it is not easy, right, to prove it and all, right? It's complicated. So we will just learn these greedy technique to understand, okay, they exist, but it will be difficult, right, for us to use it and show optimality for problems. For most instances, right, greedy is useless. So hence I just wanted to make the point that greedy is useless in most cases, but there are some problems where it works and it will give you optimal solutions. Okay. At least for this problem, it failed. And there are, thousands of other problems. It fails miserably. Okay, next. So here is where the greedy works, right? Minimum spanning tree problem, MST. So before we go into the solutions, we want to understand the problem. So what is this problem? Minimum spanning tree. You are given a graph, right? So the idea is you are given a graph, nodes and edges, and you are given weights on these edges. So it's a weighted graph. Your aim is to find the cheapest possible way so that there is a path between every pair of points, right? So cheapest way to connect every pair of points or nodes. Okay, that's your problem. Okay, so let's dig this problem further. So we will see the applications of this later once we understand all these phrases, right? What is a tree? What is a spanning tree? What is a minimum spanning tree? And then we will come to the application of it. So here is a graph, a simple graph, a complete graph with 4 nodes. And here are all the spanning trees. So now can you tell me what is a spanning tree? It is a tree that connects every node in a graph. That's it. That's your spanning tree. It is a tree. And you know what is a tree, right? N nodes, n minus 1 edges, and they're connected. So that's your tree. And if it covers all nodes in the graph, that's it. That's your spanning tree. Spanning means it spans, it covers every node in the graph. And there are a lot of spanning trees for any given graph, right? Several spanning trees. So each spanning tree, I mean, if we are considering a weighted graph, each spanning tree will have different weights on these edges. If you take the sum of all the weights on these edges, suppose this was 1, 2, 3. So 1 plus 2 plus 3, right? 6 is the cost of this spanning tree. Suppose this was 1, 3, and maybe 10. Then the cost of this spanning tree is 1 plus 3 plus 10. Sum of weights on all these edges. So you can have cost of different spanning trees. Now take the spanning tree that has the minimum cost. That's your minimum spanning tree, right? MST. Make sense? So for a graph, there are a lot of spanning trees you can create. And what is a spanning tree? It is just a tree such that it covers every node in the graph. Okay. And for a spanning tree to be present, you need to make sure that the graph is connected, right? If the graph is not at all connected, you cannot have a spanning tree. Simple, right? Okay, so there are different spanning trees. We can define the cost of a spanning tree as the sum of the weights on the edges of that tree. So we have different weights for different spanning trees. We want to choose that spanning tree that minimizes the cost. Okay, what is the application of it and why do we care for this, right? Why do we care for this? So I'll give you 3 examples. So one is, say, internet. And maybe this electricity grid. Next is water pipelines. Right? Okay, let's take internet as an example. So we know that internet, can be considered as a graph, right? The wires, it can be wires or connections between 2 computers can be considered as an edge. All computers or devices can be considered as nodes. So you have a graph. Suppose you want to connect all these, say, billions of devices such that there is a path between every 2 computers, right? So that they can communicate. And what do you typically do? You group a couple of computers, right? Maybe something like this. Look at this. So this is a spanning tree. That means from any computer can talk to any other computer. So there is a path, right? Suppose this wants to talk to this one. This is the path. Right? So the entire internet, so we can have a MST for it, minimum spanning tree, such that packets or messages can get transferred from one computer to another computer. And these can be considered as routers and so on. The aim is to minimize the total cost. Here, cost can be time, cost can be the real cost, the value, right? The money, right? It can be anything. Okay, then electricity grid. Again, homes, offices, schools, so on are the nodes here. And what is the electricity grid? Again, so you can think of this as an MST. See, you don't see wires between every 2 homes and all, right? So you will have a grid. So maybe you will have something like routers here, right? Transformers which can right, regulate all this electricity and so on. Consider water pipelines. Same thing. You will have an MST, right? Like your electricity grid or internet. So this is a very important problem. MST is a very important problem. Right? Okay. And even the road networks, you can consider MST there. Right? Okay, so there are several algorithms proposed, right? Brook's algorithm, Jarnik-Prim's algorithm, Kruskal's algorithm. We will cover only this algorithm, right? Jarnik-Prim's. This is also called Prim's algorithm, but the original discoverer, right, was Jarnik. And then Prim rediscovered it maybe 20 years later, right? So let's call it Jarnik's algorithm. So what is the idea behind Jarnik's algorithm? So here you want to construct a tree. You know that MST is a tree. So you just need a tree. The way you construct a tree is node by node, vertex by vertex. So how many nodes are there? There are n nodes in an MST, right? N nodes. So in contrast to divide and conquer and dynamic programming, we will not explain these algorithms in a recursive way. We will just give non-recursive versions of these algorithms. Okay, we'll just give non-recursive versions, but you can write recursive versions. Okay, so as I said, MST is a tree. Tree has n nodes. Let's start with any node. Any node is like, I mean, you can start with any node. Arbitrary vertex or node can be inside this tree. And then we will have a loop, n minus 1 times. So this V means the number of nodes. For n minus 1 times, what you do is you add the shortest edge, right, between the tree and the rest of the tree. So the idea is this. It's a very simple idea. At the ith iteration, you have the evolving MST, right? That MST will be evolving. And you have this tree and the rest of the tree. That means you can consider this as V minus T, right? V is the total number of nodes or vertices minus tree. So these are all the nodes, right? So there will be some nodes in the tree, some nodes not in the tree. In the ith iteration, what happens is, see, there are a lot of edges which have one end point in the tree and one end point outside the tree, correct? What you do is choose that edge that has the min cost, shortest edge, or the min cost among all these edges, right? And pull that vertex into the tree. Pull that edge as well as vertex. So there is one edge here and this vertex into the tree. And repeat. That's it. That's it. So you have one for loop, right? That runs for n minus 1 times. In every iteration, what happens is there will be a couple of edges such that one endpoint of the edge is in the tree and one endpoint will be in the, outside the tree in the remaining nodes. You find the min cost of all these weights, right? Edges. Take the shortest edge and pull that shortest edge inside the tree. That means that vertex also inside the tree and update the edges. That's it. And repeat. So in every iteration, you'll be pulling in one edge, one node. At the end of n minus 1 iterations, you will have n minus 1 edges and then n nodes because you already started with one node here, right? Makes sense? So that is the very high level idea. Okay, so let's see the working of this algorithm using diagrams. So here is your weighted graph. A, B, C, D, E, and the weights are given. we will assume that all the nodes that are in the red color are in the tree, that are in the white color, right, are not in the tree. Simple. And let's start with A. Arbitrary vertex, but we will start with A. A is in our tree. Okay. And so what is this pair here? Pull this down. So what is this pair here? So this means the distance of this node from the tree. And this one means what is the parent node that I am connected to, right? What is the other node or vertex that I am connected to? That means this vertex is connected. So initially, right, no vertex is connected to any other vertex. So we will just have a dash, we will start with 0 everywhere. But now, once we added this vertex A into the tree, what happens? So B is connected to the tree with a distance of 3, and B is connected to A. You can consider A as the parent of B, something like that, right? Because A is connected to B. Then D is connected to A, D is connected to A at a distance of 7. Is C connected to the tree directly? No, C is not connected to tree, so infinity, and there is no parent right now. Make sense? Okay, now think about all possible edges coming out of the tree. So that is these two, right? 3 and 7. 3 and 7. So what is the shortest edge? So as I said in the diagram, right? You have tree, you have V minus T tree. So find all the edges and take the shortest edge and pull it to the tree, right? So 3 and 7 are the edges. Take the shortest edge between the tree and V minus tree. So B will be pulled in to the tree, right? Now let's move one step further. So does this make sense? See, now B is pulled into the tree. See, after one iteration, now B is in the tree. A was in the tree, now B is also in the tree. Once B is in the tree, you will need to update the edges, right? You will need to update the edges. Now let's think about it. So B was pulled in, okay? Now let's think about C. C was unreachable first from A, but now B is also in the tree. Now C is reachable from this tree, right? Because C is reachable from B at a distance of 4. So now C is reachable, right? C is at a distance of 4 from B, and B is inside the tree. What about D? D was reachable from A at a distance of 7. But now there is an edge between B and D also, right? Now what you do is you compare. So D is reachable from B at a distance of 2. D is reachable from A at a distance of 7. Which of these is smaller? This is smaller, so you will update the values of D, right? So D is reachable from B at a distance of 2. That means if you can reduce the values, you should reduce the values, right?
Professor,
Because-
question.
Yes.
So here you see D, right? Is the parenthesis 2B. Why? I think there should be another option like D7A, right?
Right. So what we said is we are trying to update. So think about this. for every vertex, we are storing the value.
You have already found the shortest.
So yeah, we have pulled in B, but
Yeah.
now we are updating all the distances. See,
Yeah,
this is
what?
the updated distance.
Okay.
You can say it is the nearest distance
Okay.
from tree.
The tree. Okay. So my question is to clarify. So the remaining vertices, they are not exclusive, but just include the shortest distance from the tree to the vertices.
Correct, correct.
Okay. Okay. Thank you. That's my
Right,
question.
right. So you want to find the nearest or shortest distance from the tree, always, right? And also at the parent vertex. Okay. Hence, we updated the value of D. So think about this. C was infinity, right? Now C is reachable because we updated the distance to 4. So initially D was at a distance of 7 from the tree. Now D is at a distance of just 2 from the tree. So we will update the distances every time. Okay. E is still unreachable. Make sense? Okay. Now B is in the tree now, right? So what do? Let's think about all possible edges coming out of the tree. This one, this one, this one, right? So what do? We take the minimum one. So 7 is anyway not there, right? See, in our list, 7 is anyway not there. So we don't need to consider this at all. So just look at this, 4, 2. So what is the smallest one? 2. So we will pull 4 in, D in inside the tree. So if you pull this vertex D inside the tree, what happens then? So D is reachable now. D is inside the tree. See, all the red edges and red vertices means they are completely inside the tree. And the blue edge means that it is the shortest edge between the tree and the outside world. Make sense? Okay. Now let's see.
Professor, a question. If that is the case, why the DE is not blue?
Okay, repeat again. D.
So here you see the 4 is the shortest between the tree and all the remaining vertices, right?
Mm-hmm.
If that's the case, BC is 4, DE is 4 as well. So I believe here the blue should be covering DE as well.
Oh, you mean in the previous step?
No, then just this graph, the third graph, right?
Okay. So in the
So
third graph.
so here we see here you if you look at the remaining vertices, the second column, the third row, right? It's C4B and E4D. So both C4B and E4D should be blue such that because they are equal, right? So 4,
Good,
there's
good,
no
good. Very good, very
right.
good, very good. Yes. So what you're saying is, see, once we pulled in D, C is reachable via B, right? From B
Yeah.
at a distance of 4, and E is also reachable from this tree via D at a distance of 4. Why don't we pull in both? Yes, I mean, you can arbitrarily choose. It doesn't matter. Right?
Okay.
When you have these kinds of dilemma, that means there are 2 minimum distance, you can pull in only one arbitrarily. You can break the tie arbitrarily. Okay, why? Why is that? The reason is, as we saw earlier, there is no one unique spanning tree for a graph, right? There can be multiple spanning trees for a graph. Similarly, there can be multiple MST for a graph, minimum spanning tree for a graph, with the same cost, with the same minimum cost. Got it? So there can be multiple minimum spanning tree for a graph. So there can be multiple solutions, right, that give you the same minimum cost. So here we are interested in just one minimum spanning tree. You could choose E also, doesn't matter, right? That will also give you a minimum spanning tree, but C also works. Make sense? If you face these kinds of dilemma, choose the vertex arbitrarily. If there are multiple shortest edges, choose the vertex arbitrarily. If you want, you can choose E4D. You will still get an MST. It might be different or it might be same, right? But you can do that, right? But as we are doing it in a for loop, iteration by iteration, one vertex by one vertex, right? We will choose only one. But you can break the tie in any way you want. Yes, very good point. So here we will break the tie by choosing C. Maybe we want to do it in the alphabetical order, okay? So we choose C here. If you pull in C, now you can update the value of E, but will it decrease the value? No, it won't decrease the value. The value of E, the distance of E from the tree remains the same. See, when you added D, only then the value of E was updated from infinity to 4. So from here to here, it was not updated at all because, right, the shortest distance is still 4 from the tree. Make sense? So when you have only single vertex, again, pull that in. E4D. So this is your spanning tree. Look at all the red edges. It's a spanning tree, right? There are 5 nodes and 4 edges. It's a spanning tree, and it is the minimum spanning tree. Suppose you had chosen E4 comma D, E4 comma D instead of C4 comma B. What happens then? You still have the same option, right? If you choose this one here, you will choose C4 comma D, B later. So it is the same spanning tree. So here you did not get multiple solutions. So does this make sense?
I think I'm going to have to watch this video a couple of times before I can say yes to that question.
Right. So this is very confusing, right? Because the updating of the distances of the nodes from the tree, you need to be very sure, right? For example, D, let's look at D. D was at a distance of 7 from A here, right? So this was our tree, and this was the rest of the tree. D was at a distance of 7 from the tree. When we pulled in B into the tree, now the tree is evolving, right? This is our tree, and this is the rest of the tree. Now look at the distance of D. 7 or 2. We updated the value as 2 because the nearest vertex to D that is inside the tree is not A, it's B now. Hence, we updated all these values. Suppose we do not update the values. What happens? Suppose we did not update 7 to 2. Then maybe C of 4 comma B will be considered next and not D. That's incorrect, right? Right? So that's incorrect. So hence you need to make sure that whenever you pull in a vertex inside a tree, you need to update the distances of the other nodes. Okay. So that is the most complicated part. Once you update the distances, then it becomes easy. See, updating the distances is the most complicated part here. Apart from that, take the minimum here, that will be B, and take the minimum value here, that will be the next vertex to be pulled in. Take the minimum here, anything, maybe this one. Take the minimum, right? So taking the minimum is dead easy. It's the updating the values or distances and the parent vertex that is very complicated here. Complicated in the sense, right, if you're working with a complicated graph, it can lead to a lot of confusions. Okay. Now let's try to see the same algorithm on a different graph. Now you tell me, right, what are the next edges that will be considered? See, suppose we start from this vertex. This vertex is in our tree. Now look at all the edges that are going outside the tree. 4, 14, 26. What is the min? 4. So choose 4 inside the tree. Now your tree is this. Look at all the edges, 18, 12, 14, 26. So can you tell me which is the shortest edge? 12. So pull in this edge 12 into the tree. Now our evolving tree is like this. Now consider all the edges that are going from the tree to outside the tree. 18, 2, 3, 30, 26. What is the shortest? 2. Let's pick 2. So this is our tree. Now look at all this. See, once you pulled in 2 here, 18 got vanished, right? Because that is an edge between 2 nodes in the same tree. We will not even consider such vertices, right? So this got vanished. This will not even compete in the next round. Make sense? See, 14 was here. 14, this edge vanished in the next round because it will be like having the edge between 2 vertices in the same tree. And we are only considering the edges between the tree and outside the tree, right? Okay, now what is the shortest edge? 3. So 3 gets pulled in, and so our graph will be something like this. What is the shortest edge? 5. 5 gets pulled in, right? So what is the shortest edge? 16. 16 gets pulled in. So this is our spanning tree. Minimum spanning tree. Okay. See, another observation is this. If the edge weights are unique, you will have a unique MST. It's an important statement. I repeat, if the edge weights are distinct, if there are no duplicates, right? No repeated values in the edges, then the MST is unique. Unique. Got it? So that means you need not start from this vertex. You can start from some other vertex and still get the exact same answer. Exact same answer, right? You could have started from this vertex, it doesn't matter, right? You could have got the exact same answer wherever you start from. Okay. Next, let's consider one more graph, right? See, the more problems you work with, it will be easier for the analysis, right? So this is in your tree. Now let's look at the shortest edge going out of the tree, 29. So 29 is pulled in, right? Among this, so which is the shortest one? 31, 31. the shortest edge. 31 is pulled in. Okay, next. So the collection of these dots, right, crosses the edges. All those edges are the competing edges. So among 33, 44, 18, 9, what is the shortest? It's 9, right? So 9 will be selected. 1 will be selected in the next round. See, 1. So in the next round, which one? Is it 14? Right, 14 will be selected. And I mean, keep doing this, right? 3, 3. So here then 20, 20, 20 will be selected, and so on. 33 and 48, 33. Make sense? So this is your Jarnik's algorithm. So this is a greedy algorithm, right? At every step, you are choosing the best edge. Here, the best edge is the shortest edge. The collection of shortest edges, every iteration, will it lead to MST? Yes, of course, there is a proof. Now, this is one of the finest examples of greedy approach, right? MST. But as I said before, if you apply the same greedy approach on our coin change problem, it doesn't work, right? It might not work depending on the coin denominations. And what is the best algorithm we saw for coin change? We looked at a dynamic programming algorithm, right? That will give you an optimal solution. That will give you an optimal solution. Yeah, if the solution exists. Okay, if the solution does not exist, it will not give you, definitely. Right. So again, there are more examples, right? We will skip this anyway. Now let's look at the pseudocode again. Now this pseudocode will have some more details. So initially we looked at some 4-line pseudocode, right? It was a simple way to understand the algorithm. Now we will stuff in more details. Okay, so here is our pseudocode. T means the tree. So T is equal to VT, comma, ET. The vertex set of the tree, the edge set of the tree. G is equal to V, comma, E is the vertex set of the graph, edge set of the graph. And output will be this tree, right? That is VT and ET. That will tell you the minimum spanning tree. Okay, so initialize VT to some arbitrary vertex. We have chosen V0. I mean, you could have chosen Vn minus 1, whatever, right? We have chosen V0 here. ET is empty. Initially, there are no edges. You just have one vertex in your tree. Then you have a for loop that runs for n minus 1 times, and in each iteration, you will pull in one vertex and one edge into your tree. Let's see how we do this. You find a minimum weight edge, right? Shortest edge, such that one endpoint is in VT, another endpoint is not in VT. That means the another endpoint is in V minus VT. Among all possible such edges, you choose the one that has the shortest edge weight, right? So there can be multiple edges like this, such that one endpoint is in the tree and one endpoint is outside the tree. Among all those edges, you pick the shortest edge. Then what you do is, U star is outside the tree, right? here, look at this, U star is outside the tree. Pull that U star into the set of vertices of the tree and pull that edge itself, E star, into the edges of the tree, right? So that's your pseudocode. Now you might have a question. This is fine, right? Union, I mean, adding one more thing into the set is fine. Adding one more edge into the set is fine. This is fine. Looping is fine. How do you implement step 4 here? How do you implement step 4? You will use a min heap. Why should we use a min heap? So the reason is, look at the beauty of this. You have a collection of edges such that one end point of the edge is in the tree and another end point of the edge is outside the tree. And among all these edges, you pick the edge with the smallest edge weight, minimum edge weight. So what data structure will help you to do this? You have a dynamic list, right? I mean, dynamic set, and you always want the minimum. You can use a min heap, right? That's what we will do. Okay, why didn't we use a balanced search tree or something like that? That will also help us in solving the problem, right? Yes, it will. But it is a very generic data structure, right? Balanced BST is more powerful than min heap and more generic than min heap, and of course, a bit more slow than min heap because of this generality. If min heap solves the problem, why should we go with balanced BST? I mean, we can use BST. There is no problem with that, right? It will work. However, why care for a much more heavy data structure when we can solve the problem with a lightweight data structure? Min heap is a lightweight data structure that can solve the problem here. So let's use min heap. Okay. So how do you store the items in this min heap? So we will store the key value pairs. And what is the key? What is the value? Key is something like this. Look at this diagram. So this is your V. This is your VT. Let's say VT, tree, right? Or, okay, let me just write it as T. Tree, this is tree. This is graph minus tree. And you have a lot of these edges between the tree and outside the tree, right? So you will store all these things. So in a min heap, right? So all this G minus T in a min heap. And what is the key here? Key is the distance to the nearest vertex in VT. All these distances are the keys. See, if you want to find the minimum distance, right? You want to find the minimum element in this min heap, right? So distance has to be the key. And what is the value? Value is not that important. I mean, if you just want to find the minimum, value is not that important, but it's good to store. Okay, so what is the value here? Nearest vertex in V. So nearest, suppose this is A, this is B. So B's parent is A. That means B is reachable from A here. Nearest vertex in V. So A is the nearest vertex to B. right? That's the meaning of this. Okay, so we store key value pairs in this min heap. Now let's look at the updated pseudocode. See how we showed 3 types of pseudocodes, right? One, the first style of pseudocode, it was just 3 or 4 lines, just to give you a very high level picture. The second style of pseudocode we used had some more details, but it was still at a, abstract level. This is the third style of pseudocode for the same algorithm, but with more details. Now this, see this pseudocode thing, right? You can use it at multiple levels of information, right? And multiple levels of abstraction and details, right? Implementation details. Okay, now let's look at this graph. So we have this graph. So, and you want to find the MST of G. For each vertex you do u dot distance, u dot parent is infinity null. Why? Initially, every node is at a distance of infinity from the tree, and the parent vertex is null initially, right? And then for the starting vertex where you want to start from, you will initialize that as 0, right? For one of the vertices. So let's call that as the tree root. For one vertex, you will initialize the distance of 0. One vertex is in the tree now. Okay, then heap is V. So as I said, you want to keep V minus T in your heap, right? So so heap is initially V. While heap is non-empty, how many times this will run? Definitely n minus 1 times, n minus 1 times. Why? So every time you pull in one vertex, right, you are decreasing the size of the heap. And see, every time you will be pulling in one vertex. Let's see. U is equal to heap dot delete min. So what will this give you? So this will give you a vertex that is the nearest vertex to the tree, right? Okay, let me draw an expanding tree. When you call this delete min, it will give you one vertex that is nearest to this tree. Nearest vertex to tree, right? So U is that nearest vertex to tree. Okay, once you got it, you want to pull this U inside the tree. And how do you do it? Right? Let's see. For each, so you want to pull it inside this, and you want to update the distances also, right? Update the distances. So how do you update the distances? For each vertex V adjacent to vertex U, assume that you have pulled in, right? You have pulled in that U. Now you pulled in that U. That means you want to update all these distances. So update the distances of all the nodes that are connected to from U. So for each vertex V adjacent to vertex U, right? If V is in the heap, that means it should be here. So heap means V minus T. Right? If the adjacent vertex is inside the tree, do you care for updating? You don't care, right? So if the adjacent vertex is in the tree, you don't care for this vertex, or you don't care for this edge. If it is in the heap, only then it tells you that it is outside the tree. it should be outside the tree, and the weight, this weight, should be less than its previous weight. See, each node will have some previous weight, right? V dot distance. The updated weight should be less than the previous weight. Only then you will update it. The latest weight should be less than the previous weight. Only then you will update it. So V dot distance will be initialized to this latest distance that is reachable from the vertex that you just pulled into the tree. And V dot parent is you. See, this is how you will remember the relationship of this tree. That means V and you are connected in this spanning tree, right? You and V are connected. Similarly, V and something else will be connected. So on. If you just follow this parent relationship, you will get the entire spanning tree. Make sense? Set V with parent information, right? See, this is slightly complicated, and I want you to go over all these details again. So the point is, you understand the first two types of pseudocodes we explained, right? But for finding the minimum edge weight or shortest edge, we are replacing that concept, or we are implementing that idea using a heap. And the heap always stores, right, the vertex, the distance, okay, so let me say this. So it will store for any vertex u the nearest distance from tree, right? And right, this is your key, nearest vertex from the tree, and then the parent vertex of u. That means the vertex inside the tree from which u has the nearest distance, or the nearest vertex of you inside the tree from you, right? So that will be stored here in the parent vertex. Okay. So that's about Prim's algorithm. So this is the Prim's algorithm. And what did you use here? You used a heap. Heap is the data structure, min heap, right? Okay, we will probably not cover Kruskal's algorithm. I mean, if we have time, we will come back to this later. Okay, let's move to Dijkstra's algorithm. So this is a new problem now. This is not the MST, shortest path problem. We are given a weighted graph, right? Weighted directed graph or weighted graph. And we are given a source node. We want to find the shortest path cost to all other nodes or vertices in the graph. How do you do this? Right? So we have a graph G, and we have a source node. This is the source node, right? We want to find the shortest path cost, right? Shortest distance to each and every node in the graph from this source node. So how do you solve this problem? So there are many variants of these problems, right? So it's called one-to-one. That means there is one source and one destination vertex. Find the shortest distance, shortest path. One-to-many. So you are given one source multiple, or you can say all destinations. That's what we are attacking here now, right? Find the shortest path cost to all other nodes in the graph. It is one to many. And then many to one, many to one. So all nodes are the source points, right? All source points and one destination. One destination. How do you solve this? And then many to many, many to many. That means all source points and all destinations. That means you want the shortest path from I to j for all I comma j. So that is many to many version of shortest path. See, there are multiple versions here. And here we are focusing on one to many, right? One to many. One source vertex, all destination points. Okay. So Dijkstra's algorithm, this is a very famous shortest path problem for this one to many variant of shortest path. And let's see how this algorithm works. Before we go into the details, we looked at length Jarnik's algorithm, right? That Jarnik's algorithm is extremely helpful in solving this Dijkstra. You can say Dijkstra's algorithm and Jarnik's algorithm are sister algorithms. If you understand one algorithm, you can understand another algorithm, as quickly as possible, because the differences are kind of minimal. There are so many similar ideas, right? This also uses a tree. This also uses a spanning tree. We call it as shortest path tree. This also uses a min heap, right? The style of this, the template of this algorithm is very, very, very similar to Jarnik's algorithm. And you will see the difference, right? There is only one tiny difference. Apart from that, everything else is the same. Okay, now let's see. Dijkstra's. At a high level, what is the algorithm? Shortest path cost, right? Here we are interested in the cost. Let's say dv for every vertex. So here also we will create a tree. We will not call it as a minimum spanning tree. Here we will just call it as a shortest path tree. This is also a tree, shortest path. So what do you mean by a tree? So in this tree, from the source vertex, right, we go to different other nodes. But this is a tree. Hence, we call it as a shortest path tree. From this source, we can go to every other vertex in the shortest path, in the shortest path cost, right? Hence, this is called a shortest path tree. We will construct this shortest path tree. Again, it's very similar to Jarnik's. Look at this. For I is equal to 1 to n minus 1 iterations, add to t the ith nearest vertex to source t. So what's the difference between this and the other algorithm, Jarnik's? So there we said add to t the nearest vertex to the tree. And here we said nearest vertex to the source. That's it. That's the difference. There we always compute the nearest vertex to the tree. Here we consider the nearest vertex to the source point. Done. That's the difference. Okay. Let's see an example. It will look very, very similar to the previous example. I mean, we are considering the same graph, I believe, right? The structure is similar. The analysis is similar. Just the way you update the distances will be different. Okay. So we will see that. A is in your tree. Okay, A is in your tree. This is also an evolving tree, right? This is the shortest path tree. A is inside this, fine. Now look at all the vertices and compute the distances from the source, right? The second value is still the same, the parent vertex. There's no difference in the concept with Jarnik, but the difference is in the distance, what distance you store. This distance is not the distance, nearest distance to the tree, it is the nearest distance to the source vertex. I mean, we assumed that we should always pick one source vertex, right? We will always pick this starting vertex. Suppose this is our source vertex, source. We could have started MST algorithm, right? Jarnik's algorithm from any vertex. But here, you should always start the algorithm from a vertex given to you as a source vertex. Okay, that's another tiny difference. So here we are saying that A is the source vertex. Let's start from A. And B is reachable from A at a distance of 3, and its parent is A. D is reachable from A at a distance of 7, right? Parent is A. C and E are unreachable. Okay, this is simple. Next. Again, so look at the min distance, B, right? You will add B. Once you add B to your tree, you will need to update the distances. Let's see how we update the distances. What about C? C was unreachable from A, right? Unreachable from A before. Now, is it reachable from A now? You need to consider the expanding tree, right? Is it reachable from A now? C
Yes.
is immediately reachable from B, and B is reachable from A at a distance of 3, right? C is at a distance of 4 from B. B is at a distance of 3 from A. So C is reachable, right? So C distance will be updated as 3 plus 4, right? And its parent vertex is B. It will connect to B. It cannot connect to A, right? It's impossible because there is no direct edge between C and A, right? It has to connect to B here. Okay. Then what about D? Let's see D. D was at a distance of 7 from A. Now what you do is this. So D was at a distance of 7 from A. But now you check whether D and B are connected. D is connected to B. D is connected to B, right? At a distance of 2. And B has a shortest distance of 3 from A, right? Connected means direct connection here. A path, so this tells you that the path, the shortest distance is 3. So that means that D is reachable from A at a distance of 5, right? At a distance of 5. So 5 is better than 7. 5 is smaller than 7. So we will update this 7 to 5, right? We will update this 7 to 5 via B because its parent has to be B. So 5 comma B. So does this make sense?
Yes.
Consider in prims How did we store the distance of C and D there? In prims, how did we store the distance? C was at a distance of 4 from B, right? D was at a distance of 2 from B. We were just looking at the nearest distance from the tree. So in Jarnik's algorithm, we stored the distances like this. But here in Dijkstra's algorithm, we don't care for the distance from the tree. We care for the distance from the source vertex. So if you look at it, it is, right, there is this overlap 4 and 4, 2 and 2. However, this was the distance of B, right? And this was the distance of B. Make sense? That comes from here. Anyway, so I will not go into all these details, analyze this, right? Compare this example and Jarnik's example also, right? Compare how we are updating the distances. Okay, now we have these two. And look at this. So the distance here is 7, the distance here is 5. So what is the minimum? D here. So pull in D. Pull in D. So D of 5 comma B. Okay. Now let's see. C is 7 comma B, D is 5 comma B, and E was unreachable, right? Okay, now we just need to look at C and E. Now let's see. So C is reachable from D at a distance of 5, and D is connected to A, right, at a distance of 5. C is connected to D directly at a distance of 5, and D is that correct? Wait a minute. So
That's one of your consideration, right? But another consideration is C by B connect to A, right?
oh, right. So there is one more here, right? Yes. So wait a minute. I mean, just a minute. So C was 7 comma B, right? 7 comma B that we already considered, right? And 7 comma, right. So the point is you still consider, you can consider that, right? So from here, if you want to update, see, once you pulled in D, so C is at a distance of 5 to D, and D is at a distance of 5 from A. So 5 plus 5 is 10. Now, will you update this 7 to 10? No. You will update this only when it is smaller than 7, correct? So here you do not need to update this. Okay? I mean, you will always compare. You will update it only if it is smaller. Similarly, E to D. Now, okay, let's see. E to D is 4, right? E to D is 4. D to A was 5. So 4 plus 5 is less than infinity. So update. I mean, we should always compare only if it is lesser than. I mean, for C, we got we got something like this, right? 10 comma D. but this was not smaller than 7, hence we neglected it. So we compared E of infinity comma minus with E of 9, 4 plus 5, comma D, that was better than infinity, hence we considered this. Make sense? We always compare. If it is smaller, only then we will update. Make sense? Okay, what is the smallest one here? 7 or 9? 7. So next vertex that will be pulled in will be C, 7 comma B, and finally it will be E here. Make sense? So go over this example and compare it with Jarnik's algorithm, right? What are the exact differences? The differences are majorly in the distances, right? So you should be very careful how you update these values. So you can try out these examples also, right? But Dijkstra's algorithm requires a lot of attention because it, compared to prims, I mean, there are many similarities, but it's more complicated. Dijkstra's is more complicated because you need to add the distances here, right? In Jarnik's algorithm, you were not adding the distances. You were just comparing the two values and taking the min. But here you need to add and then take the min, right? So it's slightly more complicated. Okay, so that's about Dijkstra's algorithm. So we are done with greedy algorithms. So the questions will be of the form, you will get a graph, and either you will get a source vertex or the starting vertex you can select from. I mean, at least in Dijkstra's, and in MST, you can choose from arbitrary vertex, or we will specify that, right? The vertex you need to start from. And you need to update all these distances one by one, distances and parent vertex, right? One by one, and show, you know, the step by step. We might give you a proper template to fill in all these distances and parent vertex, right? But that's how the problem solving will be, right? Majorly Prim's algorithm or the Jarnik's algorithm and Dijkstra's algorithm. Okay, fine. So we will stop here. So go over these problems and try to apply this kind of styled distances and parent vertex for all these graphs also, right? To analyze which vertex is the parent of which vertex, how are the distances updated, and so on. So the distances are shown here itself, right? See, different diagrams might have different ideas. So we will try to give a formal template where you can update the distances and parent vertex in the problems. Okay, fine. We are done with greedy algorithms.